I know that there are probably many of you out there who are wondering, when are we going to graph logs? Well, today is the day. So as I've mentioned quite a few times now, logs and exponentials are, of course, inverses. There are a lot of properties that inverses mean. We saw some yesterday with those rules of how you could simplify. And then when it comes to graphing today, we are actually going to follow a very similar procedure that we did for exponentials. It's all going to be about determining the value of b, whether it's growth or decay, counting the number of transformations, specifically reflections. If there are no reflections, something that looks like growth will stay growth. If there's one reflection, something that's growth will become decay. And then if there are two reflections, something that's growth will stay growth, and you can't have more than two reflections. The process also works for decay. So in order for that to best work, you have to make sure you know what the two look like. So over here on your left, this is the logarithmic growth. Over here on the right, this is your decay. How will you know that it's one versus the other? Well, for decay, your value of b must be between 0 and 1. And for growth, your value of b must be greater than 1. Instead of having horizontal asymptotes like the exponentials, all logarithms have vertical asymptotes. So I would go ahead and put them in. There is a vertical asymptote here at x equals 0, and there is also a vertical asymptote here at x equals 0. And again, I think you can read it, but just in case, this is where b is greater than 1, and this is where b is between 0 and 1. So at least that part is the same as exponential as far as determining growth or decay. Again, underneath, I summarize what I just mentioned there about reflections. So if there are 0 reflections or no reflections, the original growth or decay stays the same. If there is only one reflection, then growth becomes decay and decay becomes growth. Having like a set series of steps that we went through for graphing exponentials seemed to work well for people. So we're going to have a similar set of steps here for graphing logarithms. Once you determine what the b value is, once you determine the number of transformations, here is the value of a log equation you're going to look at. Notice there is a b for the base, there is an a value, there is a c value, and there is a d value. Vertical asymptote, again, not horizontal, but vertical. It is x equals 0 to start, and it can move left and right. Remember, of course, exponentials moved up and down because these are the inverses. They're going to move left and right. If you want to give yourself 100% chance of getting the right answer, you set the argument equal to 0 and you solve for x. That will always tell you the location of the vertical asymptote. In order to figure out whether the graph is going to be to the left or to the right of the vertical asymptote, in a similar way that we figured out whether exponentials were above or below the horizontal asymptote, you have to look at the value of a. The a value is in here. If that a value is positive, greater than 0, you're going to be to the right of the vertical asymptote. If that value of a is less than 0 or negative, you are going to be to the left of the vertical asymptote. Use these two values of a facing to the left or to the right to determine the domain. So again, those three things kind of go together. And then finally, the range of an exponential, or excuse me, the range of a log is always all real numbers, just like the domain of an exponential was always all real numbers, because again, inverses means opposites. It's probably too soon, but questions so far. Again, if you apply these rules and these steps in the proper order, you should easily be able to graph me any logarithm in basically 1 minute or less. So consider the following: log base 2 of x. How many reflections does the graph undergo? In order for there to be any reflections, there either has to be a negative out front, which means reflected over the y, or there would have to be a negative inside, which means reflected over the x. Excuse me. Reverse that. A negative on the outside would mean reflected over the x. A negative on the inside would mean reflected over the y. So in any case, are there any reflections in this problem? No, so there are 0 reflections. What is true about the value of b? Remember, b is the base, so that is this number right here. B is equal to 2, which hopefully you would agree is greater than 1. In order to answer question C, you have to compare your answers to A and B. It started off with B is greater than 1. That means growth. There were no reflections, so that means that it stays growth. Any questions on that? Again, same problem, now picking up on the right here. Where is the vertical asymptote? To find the vertical asymptote, you always set the argument equal to 0. So the argument is inside of the log. Let me just copy this equation over here so that I have it so we can look at it. Okay, so where is the vertical asymptote? In order to find the vertical asymptote, you always set the argument equal to 0. And in this case, it's just x equals 0. Does the graph lie to the left or to the right of the vertical asymptote? Again, the value of the argument is a positive x because of the fact that it is positive. Positive means you're going to face to the right. Facing the right of what? Well, the answer to part F means combining D and E. You are facing to the right of the vertical asymptote, which means to the right of 0. If your graph only exists to the right of 0, then your domain is 0 to infinity. And you're always going to use parentheses because, again, you're never going to touch that asymptote. You should love any range questions because range is always all real numbers, just like it was the domain for exponentials. And then to sketch the graph, here's what we know so far. So we know that there is a vertical asymptote at 0. We know this graph has to look like growth, and we know that it has to face to the right of the vertical asymptote. So the only possible way that that can happen is if the graph looks like this. Again, slips down along the vertical asymptote and then rises off to the right. If it would make you feel better, you can find some points on that graph, which we're going to do in a minute. So again, as many points as you need to find, you can, but just be mindful of what I'm asking for. One other thing, when we were doing exponential graphs, it was appropriate to say things like increasing at an increasing rate, bounded, unbounded. That language is not appropriate for logarithms. You can only be bounded if you're approaching a y value. Logarithms approach x values. Also, you cannot say for sure whether it's increasing at an increasing rate or a decreasing rate because, again, you're not heading towards the y equals. So don't use that language for logs. It's only appropriate for exponentials. So while we know that that is, in fact, what the graph looks like, let's just be sure. Now that we have that graph in front of us, is it entirely concave up or concave down? Concave down. Remember, it's only one or the other. Again, if you're not comfortable with not having any points on the graph, well, here's your opportunity to find some. So which of these ordered pairs, if any, lie on the graph? Well, how will you know? Again, here is your general equation, log base 2 of x. The first value, of course, has to be the x. The second value has to be the y. And you would just be confirming, yes, it's true, or no, it's not. So the point 3, 8, if I were to plug that point into here, that would be saying that log base 2 of 3 is 8. Is that true? No. So that is not on the graph. What about 8, 3? That would be saying that log base 2 of 8 is equal to 3. Is that true? 2 to the what equals 8? 3. So yes, that is true. So again, if you wanted to add a point to your graph, 8, 3-ish could be about here. How about 1/2, -1? That is saying that -1 would be equal to log base 2 of 1/2. Is that true? Yeah, 2 to the what is 1/2? -1. So again, if you wanted another point on the graph, 1/2, -1 could be about here. Aaron, question? Oh, you sure? And you could continue on and keep looking for points if you wanted to. What best describes the right hand end behavior? Now, a little caveat about right hand end behavior. It's not always x going to infinity. Sometimes you're going towards the asymptote. So you just have to be careful. In this case, though, this is the right hand end behavior. So you are going to infinity. So as x goes to positive infinity, where are the y values going? Positive infinity or negative infinity? Positive infinity. And the truth is, when it comes to logarithms, those are your only choices. You're only going to positive infinity or negative infinity. No. Again, that's only appropriate language for y values. Okay, what is the x-intercept? Well, how do you find an x-intercept for any function? Put a 0 in for y. So if I put a 0 in for y in this problem, I'm going to get 0 equals log base 2 of x. You could solve that problem by exponentiating both sides, like I showed you yesterday, Or if it's a quick, easy one, you can just do the loop. So if you do the loop, 2 to the 0 equals x. What's 2 to the 0? Which means that the x-intercept is 1, 0. And if you add that to your graph, compare it to the other points, makes perfect sense. Feel free to find those points before you sketch the graph if you want. If not, just make sure that everything agrees. And then finally, the y-intercept. Just by looking at the graph, is there going to be a y-intercept? No, because what's there? The vertical asymptote. But let's see algebraically why that happens. How do you find a y-intercept ever? Put a 0 in for x. So f of x equals log base 2 of 0. Your calculator is going to say, no way. Why? You cannot take the log of a 0, so you're going to conclude none. As a quick little reminder for the future, if there is a y-intercept, you are mostly going to have to find it using change of base, because you would get something like log base 2 of 5, and the only way to find that is log 5 divided by log 2. So again, if there is a y-intercept, you usually have to find it using change of base. So we're going to do a couple more just to make sure that you understand the process, but questions? Yes?
So if you have like something that's just like log 2 to the 0 or like log 2 to the negative,
Yes.
can you assume that that's like your VA without doing it?
That's your VA. If you can't find a y-intercept, can you assume it's at 0? Yeah.
Okay.
Yeah. Just as a quick little refresher here, again, I never think it's a bad idea to review the transformations. So all the transformations that we've always known are still all present and accounted for. When it comes to logarithms, the ones that we care the most about are the horizontal movements, left and right, and of course the reflections. The reflections are what tell you whether it's growth or decay, and the horizontal translation is where the vertical asymptote is. So again, those are the ones that we're the most concerned with. Showed you a couple of examples here just to make sure that it makes sense, including, take a look at this first one. I have 3 different logs of 3 different bases just to show you the relationship. This is log base 10. This is log base E. This is log base 2. Notice that the bigger the base, the closer it is to the x-axis. The smaller the base, the closer it is to the y-axis. That's just a fun fact. If you happen to, remember it or memorize it, it's just a great way for you to check your answers. Again, the larger the base of the log, the closer it is to the x-axis. Notice that they all have the same vertical asymptote and they're all pointing to the right. They all clearly represent growth. Some of them are just a little higher than the others. And again, there's infinitely many parent functions depending on what the base of the log is. Here is showing you a log where first you move it 2 to the left, so that moves the vertical asymptote. Then 2 to the left and a vertical stretch of 5. So again, I just don't think it's a bad idea to show you examples. And then underneath, you have log base 10 of x on the right. On the left, because of the negative on the inside, that is a reflection over the y-axis, so your growth would become decay. Any questions before we try a couple more? Max? Well, but you have to watch out if there's an A as well. So again, if you set the entire argument equal to 0, you won't have to guess. You'll just be able to solve. It would be... No, you're setting this in order to get the vertical asymptote, you're going to set this entire argument equal to 0 and solve for x. If A is just 1, then your vertical asymptote is negative c. But if there's a value for A, you have to incorporate both of them. And we're going to see examples like that on the back. So let's see if that answers your questions. If not, we'll come back to it. So speaking of the back, go ahead and take a look. Again, you've got 2 more equations, and we're going to go ahead and see if we can follow the series of steps and graph as many logs as we desire. So take a look here at number 2. First and foremost, are there any reflections? So check out front. Are there any reflections out front over the x? Check inside. Are there any reflections over the y? So are there any reflections for either? There's no reflection. So again, that would be 0. What is the value of b? B is the base. The base is located here. So b is 1/3. Is that greater than 1 or between 0 and 1? Okay. In order to answer part C, compare your answers to part A and part B. If B is between 0 and 1, that implies that it's decay. If there are no reflections, does it stay decay or does it change? It stays decay. Where is the vertical asymptote? To find the vertical asymptote, always you set the entire argument, x minus 5, equal to 0, and then solve for x. So x equals 5. Does the graph lie to the left or to the right of the vertical asymptote? In order to answer that, you're going to look at the inside value of x. The inside value of x is either going to be positive or negative. In this case, it's positive. Does a positive x mean the left or the right? The right. What is the domain? In order to answer the domain, you're going to compare your answers to D and E. D and E are telling you that you're to the right of the vertical asymptote. So to the right of the vertical asymptote means your domain is everything bigger than 5. What's the range of any log? All real numbers. And then sketch a graph. So again, here's what we know so far. We know that there is a vertical asymptote at 5. So draw yourself x equals 5. We know that it has to be to the right, and we know that it has to be decay. So the only way that all of those things can be true is if the graph looks like this. Again, if it would make you more comfortable to have points on it, you can go ahead and find those points. What is the graph's right hand end behavior? So right hand end behavior is over here. So as x goes to infinity, what's happening to the y values? They are going to negative infinity. In order to find an x-intercept, you put a 0 in for y. So 0 equals log base 1/3 of x minus 5. Again, in order to solve this problem, you could either exponentiate both sides, or again, if it's a simple one like this, you can do the loop. So 1/3 to the 0 equals x minus 5. Anything to the 0 power is 1. Keith, I don't think we really need our computer right now, so maybe we could put that away. Thank you. So x is 6. And again, if it would make you feel better to add that graph, point on the graph, 6, 0, I say go for it by all means. And then what is the y-intercept? So to find the y-intercept, you are going to put a 0 in for the x. So 0 equals log base 1/3 of 0 minus 5, which is negative 5. What happens if you have the negative inside of the argument? It doesn't exist, so you're going to say none. And again, that should make perfect sense because look at your graph. You clearly moved to the right. You are nowhere near the y-axis, so perfectly fine. Questions? Yes, no, maybe? Yes. Okay. All right, let's try one more together, and then I'll give you some time to practice some on your own. So go ahead and take a look at number 3. Negative 2 ln of negative x minus 3. Just to check, you guys all have these problems, right? Some of you, okay, just check. Okay, so from here, this is an ln. What's the base of an ln? Remind me. E. Remind me, what is the decimal approximation of E? It's 2.718, but as long as you know that it's 2 point something, is 2 point something greater than 1 or between 0 and 1? Okay, so again, keep that in mind. Reflections, look out front for x-axis reflections. Look inside for y-axis reflections. How many total reflections does this graph have? 2. Correct. Inside, it's a y-axis. To answer question C, compare these two answers. It started as B is greater than 1. That's growth. If there are 2 reflections, what does it wind up as? Growth. Remember, 0 reflections, you stay. 1 reflection, you change. 2 reflections, you stay. So growth became decay, which goes back to growth. Where is the vertical asymptote? So again, maybe this goes back to what Max was asking earlier. In order to find the vertical asymptote, you set the entire argument equal to 0. That includes any negatives and any multipliers. So if I add x to the right, I'm going to get x equals -3 as my vertical asymptote. Does the graph lie to the left or to the right of the vertical asymptote? Well, you're going to check out the x inside the argument. For the first time today, it is negative. So if it is negative, that means that your graph is going to face to the left. In order to answer question F, you have to compare your answers to D and E. So you are supposed to face to the left of -3. What does the left of -3 mean for domain? It means -infinity to -3. What's the range? No work required, all real numbers all the time. And then try to sketch your graph. Again, here's what I currently know. I currently know that there is a vertical asymptote at x equals -3. I know that the graph has to be to the left of that vertical asymptote, and I know that it has to represent growth. The only possible way that that could make sense is if the graph looks like this. Again, I feel confident in what the graph is supposed to look like, so I graph it before I answer the rest of the questions. Please feel free to answer the rest of the questions before you do that if it makes you feel more comfortable. And then again, pay close attention to this. What describes the graph's right hand end behavior? The right hand end behavior for the first time today is not going to infinity for the x. The x value is going to the asymptote. So you would have to write that as x goes to -3. And again, the reason why it's -3, that's the vertical asymptote. The graph does not exist anywhere past that. So as x goes to -3, where are the y values going? Up to +infinity. So again, a little bit of an interesting thing that happens here with the log sometimes. Your right or left end behavior is often not infinity or -infinity. Sometimes you're heading towards the vertical asymptote, and that's okay. Finally, the last two questions. What's the x-intercept? So put a 0 in for y. So 0 equals -2 times the ln of -x minus 3. A reminder of how you would find this. Again, if there's any algebra to do on the outside, you should do that first. And in this case, you can and should divide by -2. The base of an ln, of course, is e. The stuff in parentheses has to stay there, so don't add or don't do anything to that. When you have no more algebra to do, you can either exponentiate both sides or do the loop. So e to the 0 equals -x minus 3. Anything to the 0 power is 1. So if 1 equals -x minus 3, I'm going to add the x to the left, which gives me 1. Which gives me x, and then I'm going to subtract the 1 to the right, which gives me -4. So the x-intercept is -4, 0. And again, if you would like to add that point to your graph, it makes perfect sense. Last but certainly not least, put a 0 in for your x. You're going to get -2 times the ln of -3. This is again going to be a none. It's not always a none. It just happened to be the 3 examples that I picked, but I think both on the homework have actual y-intercepts, which again, you most commonly find them using the change of base formula. Questions? Yes. Just showing this step right here is sufficient. I mean, I guess technically, if it was on a test and you just put none because you knew it was none, that probably would be fine. But I mean, I don't know that it hurts to show the work, but yeah, I probably would accept it. So before we finish up the last page of notes, why don't you flip to the homework page, which is the back page? And why don't you try the first one at least? If you can try both, that's great, but try the first one. See if you can duplicate that series of steps. I've been saying that exponentials and logs are inverses, inverses, inverses. So I just want to reiterate to you, what does that mean exactly? So inverses, of course, another word for inverses is opposites. Here are all the things that are true about inverses. A function has an inverse function if and only if it follows the horizontal line test. By the way, every exponential and every log will pass the horizontal line test, so you can always find an inverse. If you are a function that is lucky enough to pass both the vertical and the horizontal, we would call you one-to-one. So again, all logs and all exponentials are one-to-one. When you are talking about finding equations or finding graphs, you are always swapping every x with every y, which also means you are swapping every domain and every range, which we saw today. And if you were to graph the pair of inverses on the same set of axes, they have to be reflections of each other over the line y equals x. Look at the graph examples that I gave you on the left. Here is 2 to the x, that's exponential. Here's e to the x, that's also exponential. Then you have the line y equals x, and here's your log inverse, here's your ln inverse. Again, they are perfect reflections of each other over the line y equals x. Both are growth. Look at the 2 on the right. Here is your exponential graph that was moved to the right. Here is therefore your logarithmic graph that was moved up. And again, notice that in this case, they cross, but that's okay. Still both growth. And then over here, here is your exponential equation that was moved down. If you have an exponential that is moved down, your logarithm will move to the right. And again, notice that in every instance, they're always reflections of each other over the line y equals x. If we had more time before winter break, we would probably graph both of them together. For now, graphing them separately is fine. And then how do you find the equation of the inverse? Well, there's a 4-step process, which is what we're going to do to finish up. So let me remind you. Step 1, replace f of x with y. Step 2, interchange x and y in the equation. Step 3, resolve for y equals. And last but not least, call it f inverse. Also, if we had more time, again, before winter break, we might be asked to prove inverses. Again, in order to prove inverses, you have to do f of f inverse and f inverse f. Remember, that's called composition, back from section 1.8. And in both cases, you would get an answer of x. All that's good stuff. Maybe we'll talk about it later in the year if it comes up. But for now, all I want you to be able to do to finish is find the equation of the inverse. So to find the equation of the inverse, you're going to follow that 4-step process. So take a look at number 1. I would think that it's common sense, but in case it's not, the inverse of every exponential has to be a log and vice versa. So here for number 1, let's follow the 4-step process. Step 1, replace f of x with a y. Step 2, swap your x and y. Step 3, solve for y equals. When you go to solve for y equals, that's where most of the work is going to be. Algebraically speaking, the first thing you have to do is add 8. There's nothing else you can do algebra-wise or exponent-wise, which means you now need a log. In order to create a log, you can either log both sides or you can do the loop. Again, whichever one makes more sense to you. If you're going to do the loop, you loop from the base to the other side and then back. A note about the loop. You have to start by writing the word log. The 2 is the base, and anything that you loop together has to be parenthesized. So because you looped the x plus 8 at the same time, you have to put it in parentheses. Equals negative y plus 3. Because of the fact that the y is negative, the easiest way to finish this problem is to add the y to the left and subtract the log to the right. So again, I decided to add this y over here and subtract this log over here. And in your final step, call it f inverse. That's a perfectly fine way to leave your answer, but some of you might prefer to write negative log base 2 of x plus 8 with the 3 in the back. I promise you it matters not. Both of those are perfectly accurate. I would suggest when you're done, you go back and compare it to the original. Remember, everything should be opposite, including one being a log and one being an exponential. The opposite of a minus 8 is a plus 8. The opposite of having a negative up in the exponent is having a negative out front. So again, check that everything is opposited. If you wanted to be 1,000% sure that you did it correctly, you would go back and try to prove it by doing the composition both ways. And not for nothing, but if you were just trying to check it for yourself, even if you just did the composition one way, you could feel reasonably sure that you did it correctly. So let's just finish off the last two to make sure that we can do it. Take a look at number 2. Start by putting a y in. Then swap x and y. Then you're going to resolve for y, which means do some algebra. Algebraically speaking, what's the next step? Subtract the 3. The 2 in the exponent has to stay there until you drop it down. The only way to drop it down is to either log both sides, that's what we did yesterday, or do the loop. They technically are the same thing, but I did want to make sure that I show you both. Remember, if you're doing the loop, it's from the base to the other side and then back. If you're looping with a base e, you're really doing what kind of a log? An ln. Again, you looped the x minus 3 together, which means you must put it into parentheses. And the reason why it's so important you put it into parentheses is because in the final step, when you move the 2 over, you need to make it clear that that is separate. It's not going to be x minus 5 because the x minus 3 is on the inside. That's moving you left and right, where the negative 2 is on the outside. That is moving you up or down. And again, take a minute, compare it to the original. Everything should be opposite, including the fact that 1 is a log and 1 is an exponential. Why don't you all go ahead and take 1 minute to finish the last one? So you do the last one at your seat, and I'll do it up here. Only look up once you're done. See if you can, in fact, do it on your own. Again, just take a look up here when you think you have it. Make sure that everything is opposite, the 5s, the 1s, the fact that you started as a log and you ended up as an exponential. You have to make sure that when you do the loop, you're either taking the log and making it exponential or taking the exponential and turning it into a log. Questions? Parentheses wise, when you're doing it this way, it's kind of assumed that there are parentheses here, but yes, it would be just as correct to use them if it makes it clearer for you. So that was the final lesson about logarithms, the final chapter 3 lesson. Again, I know there's been a lot. I know it's been a busy time of year. Let me just go ahead and stop my video.